Okay, imagine this. Two beams of light,
Uh-huh.
really carefully aimed, racing at perfect right angles, and then right at the perfect moment, they get stitched back together by
Okay.
like a knife edge of glass. Sounds like science fiction, right?
It really does.
But this was a real experiment back in 1887, and its result, which was totally quiet, totally unexpected, well, it just completely flipped our understanding of the universe on its head.
Yeah.
So today on this deep dive, we are getting into that experiment, the Michelson-Morley experiment.
Classic.
We'll look at how its kind of shocking outcome didn't just pave the way for Einstein's special relativity,
Right.
but also inspires this other newer idea called motion theory.
Which is fascinating in its own right.
Totally.
Yeah.
Our mission here is to unpack how this one single null result, this nothing result, from way back then, still shapes how we see reality. And we want to introduce you to this, well, alternative way of thinking about these really big ideas. We've dug into a lot of research, on Michelson-Morley, Lorentz, Minkowski, and this developing motion theory concept.
And what's really wild here, is how science often moves forward, not because someone proves a big theory right,
Yeah.
but because they find something's missing, an unexpected absence. Before 1887, pretty much everyone thought space was filled with this stuff.
The ether.
The luminiferous ether, yeah. This invisible, pervasive medium that light was supposed to travel through, like sound through air or ripples on a pond.
Made sense at the time.
It did. And scientists were pretty confident that Earth, moving through this ether would create a kind of wind.
An ether wind, like sticking your head out of a car window.
Exactly, a cosmic breeze. And they figured, with precise enough tools, we should absolutely be able to measure it. The expectation was totally clear.
So the stage was set for, well, what looked like a failure at first, but turned out to be huge. Let's picture this setup they had.
Michelson and Morley's interferometer, it was ingenious.
Right. So they take a beam of light, split it in two. One half goes one way, the other goes perpendicular to that.
Uh-huh. Off to mirrors and back.
Exactly. Off to mirrors, back they come, and recombine at a detector. And the whole point was to see if Earth, moving through this ether, messed with the timing.
Like your swimmer's analogy. One fighting the current, one going across it.
Yeah, exactly. If that ether wind existed, then rotating the whole thing, well, that should change how long each beam took.
Right, the relative speeds would differ.
And you'd see it in the interference pattern, those light and dark lines, the fringes, they should shift.
That was the prediction. Crystal clear. And then the observation.
Nothing.
Absolutely nothing. Within their ability to measure, zero shift.
Yeah.
Zip. Nada.
And they repeated it. Others repeated it with better gear.
Same result. Always the same. This silence on the screen, as people called it, it was deafening.
So that null result, that nothing, meant something huge.
It meant there's no detectable ether wind. Period. Which implied something even bigger. The measured speed of light is the same for everyone.
Regardless of how you're moving.
It doesn't matter. It's constant. And that just forced this massive kind of painful rethink in physics. It basically cornered the field into developing special relativity.
Yeah.
So this raises a big question for you, listening right now. If there's no ether, how does light travel? And maybe even deeper, what does that tell us about space itself?
That really is the core puzzle, isn't it? It just yanks the rug out from under everything you think you know.
Totally.
If light isn't, swimming through something, how does it get here from the sun? What is space then? Must have been a wild time for physicists.
Oh, absolutely mind-bending.
Yeah.
Because before that experiment, yes, space was basically seen as this material thing, an invisible stage, right?
Yeah, the backdrop for everything.
But after 1887, that whole story just frayed. The idea of space as this static, tangible thing, suddenly it just didn't hold up.
So that forced them down new paths.
Exactly. Two main roads kind of emerged from that challenge, both to explain why the speed of light stays constant.
Okay, what were they?
Well, first you had what became Einstein's road. He essentially said, okay, let's trust Maxwell's equations about light, and let's make the constant speed of light C a fundamental rule, a postulate.
Don't question it. Build from it.
Right. And then rebuild the rules of motion kinematics from scratch. That led straight to special relativity.
And the other path.
That's closer to what motion theory suggests. It also keeps C constant, but interprets it differently. Not as just a speed limit, but as the universe's maximal synchronization rate.
Synchronization rate.
Yeah, like how quickly different parts of reality can coordinate or update each other. And it sees all motion, all kinematics, as sort of rules of alignment within this fundamental structured motion.
Okay. That's a different angle.
It is. But the key thing for you, the listener, is this.
Mm.
Either way you slice it, that old idea of space as a substance, a stage, it's gone. Now it's understood more like a network of relationships.
A framework for interactions, maybe?
Something like that. It's about relations between motions, not a container they sit in.
Okay, so let's dig into that. One key figure here was Hendrik Lorentz. He provided the mathematical machinery, right?
Absolutely crucial.
Yeah.
Lorentz basically figured out the math needed to keep Maxwell's equations working correctly for observers moving relative to each other without an ether.
This is the famous Lorentz transform.
That's the one. It's a set of equations that, well, mathematically mixes space and time together in just the right way so that chi, the speed of light, always comes out the same for everyone.
It's the math that patches the hole left by the ether.
You could say that. And amazing things just kind of fall out of that algebra.
Like what?
Well, time dilation, the idea that moving clocks actually tick slower.
Right.
And length contraction moving objects get shorter along their direction of motion. These aren't just ideas. They're direct consequences of the Lorentz transform math.
Okay, so how does motion theory look at those? Is it just geometry or something else?
That's where the reinterpretation comes in. Motion theory sees these effects as more, well, physical processes happening within the objects themselves.
How so?
Take a clock. Motion theory sees it not just as a timekeeper, but as a stable loop of some kind of structured motion, like an internal oscillation.
Oh, okay.
If you change its overall state of motion, you're actually changing its internal synchronization rate compared to another clock. It completes fewer internal cycles relative to the observer's clock.
So it appears to tick slower. Dilation.
Exactly. It's about the clock's internal dynamics adjusting. And similarly for a ruler, it's seen as a kind of phase-locked lattice of motions.
Like atoms arranged in a structure.
Sort of. Change its overall motion, and you actually change how its internal phases pack together. The equilibrium spacing along the direction of motion gets shorter. That's contraction.
So it's not space shrinking, but the ruler itself adjusting its internal structure.
That's the motion theory picture. It's about the internal operations of things dynamically responding. So the Lorentz transform isn't some mystical geometric warping.
It's more like bookkeeping.
Yeah, crucial bookkeeping. It keeps track of these alignment changes so that the universe's maximum update rate, c, is never violated. Lorentz basically wrote the grammar that keeps that maximum sync rate constant.
Okay, Lorentz provides the grammar, the math, but that can be pretty abstract. Visualizing it helps, right?
Definitely.
Yeah.
And that's where Hermann Minkowski comes in. He did something brilliant.
What was that?
He took Lorentz's, somewhat abstract algebra and turned it into geometry. A picture.
Space-time.
Exactly. He showed how you could think of reality as this four-dimensional thing, three space, one time, what we now call space-time. And in this picture, the Lorentz transform rules become geometric properties.
Things like worldlines, light cones.
Right. Worldlines tracing paths through space-time, light cones showing the limits of cause and effect, proper time being the wristwatch time along a path. It all becomes this elegant visual structure where Lorentz invariance is just built in.
It makes it easier to grasp, for sure. But how does motion theory read that picture? Is it still a 4D block?
Well, motion theory keeps the picture because it's incredibly useful, but it reinterprets what the picture represents.
Okay.
So Minkowski's diagram isn't seen as a map of some literal fabric of space-time. It's reread as a map of allowed synchronization relations.
Ah, back to synchronization.
Right. Those light cones, they aren't the edges of a material sheet. They show the boundary for how fast alignment or coordination can spread, the ultimate speed limit for information.
And proper time.
That's seen as counting the number of internal resolution cycles, like internal ticks of a structure as it moves along its world line.
So the geometry isn't the thing itself, but a representation of the rules of motion.
Precisely. The geometry is like the shadow cast by the underlying rules of motion's alignment. Minkowski gave us this powerful visual tool, and motion theory uses it, but says, here's what's really being pictured, the dynamics of synchronization.
And it's not just theory. These ideas, whether you view them through relativity or motion theory, they get tested, right?
Oh, absolutely. Later experiments really hammered home the points. You had Kennedy, Thorndike, Ives, Stilwell.
What did they show?
They probed the constancy of Keating and time dilation even more rigorously than Michelson Morley. Found the same consistency.
And the Hafele Keating experiment with the clocks on planes.
Classic. Showed that clocks flown around the world ended up out of sync with ground clocks, exactly as predicted. Time dilation is real. We see it constantly with modern optical clocks, too.
And GPS, people use it every day. that relies on accounting for these relativistic effects, doesn't it?
Couldn't work without it. The satellites are moving fast and are in a different gravitational potential, so their clocks tick at a different rate than ours on the ground.
You have to correct for that difference.
Constantly. If you didn't account for both special and general relativistic effects, the time dilation, your GPS position would drift off by miles every single day. It's engineering proof baked into our lives.
So how does motion theory explain these conformations? Is it just saying, yep, relativity is right?
It agrees with the observations, absolutely. The math matches. But it offers a different underlying story for why.
Okay.
From the motion theory view, these experiments all confirm this maximal synchronization rate of the universe. Time dilation isn't just geometry, it's a real change in the alignment rate of a clock's internal workings.
Like the clock's internal rhythm changing.
Exactly. And things like gravity or velocity change the local synchronization density, how tightly coordinated things are, which affects that rate.
So for GPS.
The satellite clocks are in a region with a slightly different sync density and are moving fast, so their internal sync rates are different. You have to mathematically translate between their rate and the ground rate to get accurate positions.
Same math, different reason why it works.
That's the idea. The cause is re-narrated in terms of these underlying motion and synchronization dynamics.
Okay, this is important then. We need to be really clear about the difference between the old ether idea and this motion substrate in motion theory.
Crucial distinction. They sound similar, maybe, but they are fundamentally different concepts.
Right. Let's break it down. The old ether.
The rejected ether, the one Michelson Morley killed. That was imagined as some kind of substance, maybe particles, maybe a fluid that filled space.
Something you can move through.
Yes, and crucially, it was thought to have a preferred rest frame, a fixed background you could measure your speed against, and it might even exert drag.
Which Michelson Morley showed wasn't there.
Exactly. Gone. Dead idea. Now, the motion substrate in motion theory, that's completely different.
How so?
It's not a substance you move through. It's described more as the unresolved background motion of reality itself, the fundamental capacity for things to synchronize.
Unresolved motion.
Yeah, the base level of activity that makes up reality. And critically, it has no rest frame. There's no absolute stillness to measure against, and no drag. It's not something pushing back on you.
So it's not a fluid you can outrun?
Not at all. It's more like the fundamental tempo the universe enforces, the basic rhythm or coordination capability that everything participates in.
So Michelson Morley killed the idea of a draggy, fixed ether.
Yes. But importantly, it did not kill the idea that there might be some underlying structure to motion itself.
And motion theory says there is such a structure.
It posits that there is structure, just not a fluid one. There's this maximal coordination rate, C, and rules the Lorentz transformations that describe how things behave to keep that rate invariant for everyone.
Okay, that distinction is super important. Let's go back to the interferometer then, that 1887 experiment.
Right.
If we look at it through this motion theory lens,
Right.
why was the result null? Why no fringe shift?
Well, in motion theory, you don't think of the light in those arms as just photons flying through empty space.
You think of it as
a sync disturbance,
Yeah.
a ripple propagating through that underlying motion substrate, that capacity for synchronization.
like sending a pulse through the system's ability to coordinate?
Kind of, yeah.
Yeah.
The time it takes for that pulse to travel down an arm and back, T, is still related to the arm length, L and C. So T is roughly L divided by C. But here, C isn't just a speed limit postulate. It's interpreted as arising from the substrate's properties. Think of it like a ratio of the universe's internal synchronization pressure, its tendency to align, versus its inherent resistance to perfect alignment, a kind of tension.
Like SCORT SR, pressure over resistance.
Something like that conceptual structure, yes. Now, when you rotate the whole Michelson-Morley apparatus, you're changing your motion relative to some observer, sure, but you are not changing that fundamental SR ratio, that inherent synchronization capacity of the substrate itself, at least not locally at the scale of the device.
Ah, so the underlying speed limit doesn't change just because you turn the machine.
Exactly. Both arms of the interferometer are still constrained by the same maximum synchronization rate, the same C derived from that SR ratio.
And if both arms are limited by the same rate?
Then there's no difference in travel time when they recombine, no fringe shift. The null result becomes the expected result. It's just showing the invariance of this fundamental synchronization rate under local changes in motion.
It's the universe basically saying, my internal tempo doesn't care how you spin your little table.
That's a pretty good way to put it.
So it's really interesting how motion theory arrives at the same mathematical results as special relativity Lorentz transforms, time dilation, see invariance, but tells a completely different story about why.
It is fascinating. The algebra matches, the predictions for experiments like Michelson, Morley, or GPS match, but the underlying narrative, the physical interpretation, is profoundly different.
It's not negating the observation.
Not at all. It's aiming to provide a deeper, perhaps more mechanistic explanation for those observations. Instead of starting with postulates, it tries to derive them from this idea of structured motion.
So if the math is the same, what's the real advantage? Why bother with this different story? Is it just like philosophical preference?
That's a fair question. Part of it is seeking a more fundamental why. Why is C constant? Why do Lorentz transforms work? Special relativity posits them. Motion theory attempts to derive them.
Let's recap those key differences in interpretation. Invariancy.
In special relativity, it's a starting principle, a postulate. In motion theory, it's a derived ceiling, the fastest possible rate of coherence or synchronization update in the substrate.
Time dilation and length contraction.
In special relativity, often visualize geometrically distortions of spacetime. In motion theory, there are dynamic effects within objects, changes in internal synchronization rates or phase packing due to changes in motion.
And that invariant interval in Minkowski spacetime?
In relativity, it's a fundamental geometric property. In motion theory, it's interpreted as a conserved count, the total number of internal resolution cycles, or ticks, along a path through the motion structure.
So same math, but the symbols point to different concepts.
Exactly. Motion theory tries to ground the symbols in the behavior of structured motion itself, rather than in points within an abstract geometric container. It aims for a more, well, dynamic picture.
Okay, before we wrap this up, we should probably hit some common misconceptions. These ideas are definitely mind-bending.
Yeah, easy to get tangled up. Let's clear a few things.
Misconception number 1. People hear Michelson-Morley found nothing and think it means space is truly empty, that nothing carries light.
Right, that's a common takeaway, but it's not quite right.
Yeah.
No, something absolutely exists. It's just not a physical wind. What exists is the universe's fundamental ability to synchronize, to coordinate interactions at this maximum rate c.
It's a property of reality, not a substance in it.
Precisely, just not a particulate ether wind you can detect with a turntable. Okay, misconception 2.
That Lorentz contraction, things getting shorter, is just a mathematical trick. Like, it's not really happening.
Also incorrect. The motion theory view especially takes it very physically. It implies that the actual structure of matter, these phase-locked lattices, literally rearranges slightly. They repack their internal phase relationships.
But the math just describes that real physical change.
Exactly. The math is just how we keep accurate books on what's physically happening to maintain that constant c. It's not just a trick.
All right, third one. Minkowski spacetime. Does it make space real again? Like a tangible fabric that can bend and warp?
Another subtle one. No, not quite. Minkowski's picture is powerful for visualizing the rules and constraints. That grid you see, it's a map of allowed relationships, allowed ways things can synchronize and affect each other.
It shows the structure of the rules, not a physical structure you can touch.
Well put. It maps the allowed alignment changes, the causal structure, not a material fabric.
Got it. So this isn't just about looking back at 1887. Motion theory, you mentioned, points towards new experiments.
Yes, and that's really exciting. It suggests ways to probe these ideas directly, building on that Michelson-Morley spirit of looking for fundamental properties.
Not just confirming relativity again, but testing this motion substrate idea.
Exactly. Hunting for anisotropy or effects related to these motion variables themselves.
Like what kind of experiments?
Well, one idea is a phase index gravity analog. You could try to create a region where you actively manipulate the synchronization properties of a medium, creating a gradient.
Like an artificial gravity field for light.
Sort of. Motion theory would predict how light bends in that gradient, and you could compare that prediction to known gravitational lensing. See if the underlying mechanism matches.
Interesting. What else?
A rotating cavity sync test. Use really high-precision optical resonators, put them on a turntable. Motion theory predicts you should see no change in the resonant frequency due to orientation, beyond the standard known relativistic effects.
And if you did see a tiny change?
Then that would put limits on how truly constant that SR ratio, that synchronization property, really is. It would be a direct probe.
Okay, one more.
Maybe a clock rate equals sync rate rig. You could set up, say, two highly stable oscillators whose interaction is mediated by some controllable substrate. You'd predict how their frequencies shift as you tweak the local synchronization density of that substrate.
And compare that to general relativity's predictions for clocks and gravity wells.
Exactly. See if the motion theory model based on sync density gives the same results, or perhaps offers finer distinctions. These are ways to test the mechanisms suggested by motion theory, not just the outcomes.
So it keeps that spirit of Michelson-Morley alive, searching for the deep rules, but with new tools and concepts.
Precisely. Hunting for anisotropy, but in these motion-related variables.
Wow. So, okay, let's bring it home. What started as this quiet, seemingly uneventful experiment in 1887.
The one that failed to find the ether wind.
Right. That silent screen actually bought us this profound new way of seeing the universe. Michelson and Morley, they didn't fail. They freed physics from a bad picture.
They cleared the way.
Yeah. Then Lorentz wrote the essential math, the grammar that protected C. Minkowski, drew the picture, gave us space-time to visualize the rules. And now motion theory comes along and says maybe that invariant C is just the surface level. Maybe the deeper thing is that motion itself, structured motion, is the fundamental substrate.
Proposing a dynamic foundation.
Yeah, redefining space as unresolved structure, time as the rate loops resolve, forces as gradients in motion, gravity as things moving towards denser synchronization. It really changes the whole feel of reality.
It absolutely does. That quiet screen on the interferometer, it wasn't empty. You could almost say it was the sound of the universe keeping its own time, its own fundamental rhythm.
Yeah.
And it really asks us to think, if reality is fundamentally this structured, synchronized motion, what other silences, what other phenomena that seem like nothing are actually waiting to reveal more about the universe's true dynamic nature?
That's a great question to leave people with.
Yeah, we really encourage you to ponder that shift from thinking about a static stage filled with ether to a universe built from dynamic, synchronized motion. How does that change your perspective on what reality even is?